Hello everyone, welcome back. We will have the third case of the cantilever. We covered the uniform load, we covered a single point load, and now I will do a uniform load with an internal hinge on a propped cantilever. So inserting a hinge for construction purposes, maybe the beam cannot be put on a truck, it's so long, and that it will have to be spliced in the field. So we put an internal hinge in here, and then we would have a roller at the tip fixed at the left edge with the internal hinge, and it remains statically determinate. So let's save this as cantilever. Let's call it propped cantilever with hinged. Propped cantilever, uniform load, and a hinge in the middle here. This is demo. Let's just call it demo. Let's just hide everything here that we don't need. Let's change this icon so that it looks like a roller. Unfortunately, it's right on the beam. It's not below the beam, but that's okay. Right click, make it. I like to make my boundary conditions, green here. Make it as big as you can. A solid circle. That's our traditional roller. I'm going to hide this so that you don't think that that's a hinge. So now, and then I need to insert the position of the hinge, so I'm going to call it hinge X spot, and that will go from 0 to tip X as always. And then I will put in the hinge point. Hinge point is hinge X. Again, the hinge X did not have to be capitalized because it's just a number, a scalar, but the point in Cartesian space must have a capital letter. I used capitals on both. So here we have, okay, and then let's move that around. There it is, I could see it. I'm going to make it white and really big so that it looks like a gap. That's kind of fun. I'm going to make it really big as I can, and I'm going to make it white. And now we see a nice hinge here, nice visible hinge. I'm going to hide this one, I don't need that. So now I have a nice visible hinge. And I'm going to do two things. I'm going to get the moment in the wall from two different things. So I'm not going to draw the whole bending moment diagram, but I want you to get the moment in the wall. And I'd like you to think about this as the superposition of the moment in the wall due to this load, this vertical load going up at this roller. And then and that would be concave up. It would be compression on the top due to this. And then compression on the bottom, compression on the top due to this load. Sorry, I said it right. And then, or tension on the bottom, and then tension on the top due to the uniform load. So it's just the superposition of these two things. But what is this piece in here? Is this complicated? Is it complicated to find this reaction? The answer is absolutely not. This is an independent piece in equilibrium, and it's just a simply supported beam. With a reaction at the left and a reaction at the left and a reaction at the right, and it's just W times this distance over 2. So let me call that span 2, which is tip X minus hinge X. So I'm going to put my hinge over here. Let's make it nice and so that you could see that. It should be 12. Yeah, span 2 is 12, okay? So it's just the difference between these two numbers. The upwards reaction here has to be W times span 2 over 2. Can't be any easier. So I'm going to call that R right is W times span 2 over 2. Stop animating. Ugh. Okay, W times span 2 over 2. Let's make easy numbers here. 10, 20, maybe 100 just for ease. So that's 1,000, should be 500. Yep, it is 500. Okay, so now check this out. Let's say M wall due to R right is R right times tip. This is driving me crazy. Stop. R right times tip X. And ladies and gentlemen, that is tension on the bottom, compression on the top. We call that a happy beam because it looks like a smiley face. So I'm going to call that a positive internal moment. Compression on the top. The other one is negative because it's tension on the top, compression on the bottom. It's a cantilever. So I'm going to call that M wall due to distributed load or something, which we knew before, but I'm just going to program it again. That's W times that entire length, tip X squared over 2. But I'm going to make that negative now so that I see that it's definitely tension on the top. And then M wall final is the positive and the negative, or the superposition of these two. So M wall due to R right plus M wall distributed load. I'm looking at my cases, and I added them up because I forced the negative sign to be in the M wall distributed load. And that is 3,800, and it's on this side, so I'm going to put it over here. M wall final is M wall final foot pounds. You can draw the bending moment diagram. It's going to be WL squared over 8 in this spot, but then it's parabolic in here. It ends up here. Maybe we'll do one more video on that. But right now, the most important thing is to realize that this is super exact and really kind of amazingly easy. Let's just try any number here. As the superposition of two things, again, I have this load going up, and you could draw that in. You could even draw it to scale if you want to be super fancy. I just show you here how to do that. This would be R right over force scale. Maybe a little small. Okay, and then intersect here. Hide this. Hide this. Hide this. Hide this. Put a vector in here. Make that vector big and red. Should I go faster? I can go faster. Boom. And I could even put that in here if I want. R right is of course that's pounds in the United States here. Okay, so we have a very nice compact way of attacking the moment in the wall here, the reaction. It's variable for where I put the hinge, and if you imagine the hinge at 0, I'd have a beam 16 feet long with 200 pounds per foot. Let's just make it something simple here so we could do it in our head. 200 pounds a foot. That would be 2,000 pounds total. Half would be here, half would be here, because now we have a simple beam again, because I have a hinge at the wall. Isn't that amazing? It's kind of amazing. And then if I put the hinge out here, that reaction is 0, and I just left with the uniform load on the wall, on the beam, and the M wall final is only from there. So yes, easy, breezy, and insightful.